Okay, so this is question number 16 of the Nuclear Physics Homework Booklet. And in part A, we are told that this particular nuclei here can decay by electron capture to become an isotope of lead. And we're given an equation here. So this isotope plus an electron goes to this isotope of lead plus a neutrino plus Q. And Q is the energy that's given out in this process. First of all, we're asked to explain what is meant by electron capture. So we just have to basically say what it is. So this was worth 3 marks. So what we've got is we've got an inner shell orbiting electron. So the electron that's in an inner shell is captured by a proton in the nucleus, and it's really important that you put proton. You can't just say it's captured by the nucleus, it's captured by a proton in the nucleus. And when this happens, a proton is converted into a neutron. For part 2, we're then asked to give just one reason why electromagnetic radiation is emitted following this. Well, once this happens, the daughter nucleus or the new nucleus could be in an excited state, and when that happens, the nucleus drops down from an excited state to the ground state, and when it does that, it emits electromagnetic radiation. So there was 1 mark for just saying that, really. So that's basically exactly the same as the excited atoms that you looked at in your first year. We're then asked to simply write down another equation where this thing could also be converted into lead. Well, beta plus decay is basically a very, very similar thing to looking at to electron capture. So what happens here is that this decays into lead. It emits a beta plus particle or a positron, and also an electron neutrino. And if you write basically all 3 of these down correctly, you get a mark. So they're your 5 marks for the first part of that question. In part B, we're then told that this thing can also emit alpha radiation, and an initial or starting measurement of the alpha particle activity of this sample gives a corrected count rate of 1,200 counts per second. So that takes background radiation into account. After an interval of 24 hours, in other words 24 hours later, the corrected count rate falls to 290 counts per second. So we started off at 1200 counts per second, it's gone down to 290. And it says basically assume that corrections have been made for the radiation and dot products from background radiation. Well, since it says corrected count rate, then we should assume that anyway. So part 1, we're asked to show that the decay constant of this thing is roughly 1.6 times 10 to the minus 5 per second. So because we know that the activity changes, so it started off at a certain value and it goes down exponentially, and sometime later we've got a new activity, then we can use this equation here. Again, this is the count rate after a certain amount of time, t. This is the starting count rate or activity. Lambda is our decay constant, and t is the amount of time it took for the activity to fall down to this number. So this time we're just going to do it all algebraically. We rearrange this and we end up with this thing here for the decay constant, and then we just put our numbers in. So everything's going to be done in seconds, but we're given things in 24 hours. So we need to convert that into seconds. So t is 24 times 60 times 60, because there are 24 hours and 60 minutes and 60 seconds in one day, or in 24 hours. So we've got 1 over that time multiplied by the natural log of 290, which was our finishing activity, over 1,200, which was the starting activity. Put all of that on your calculator and it gives you 1.64 times 10 to the minus 5. So we've shown that the decay constant is about 1.6 times 10 to the minus 5 per second. We're then asked to calculate the half-life of this sample. Well, now we've got the decay constant. That's really easy, because the half-life is just equal to the natural log of 2 over the decay constant. Again, put that in your calculator, gives you 4.2 times 10 to the 4 seconds. And finally, we're then asked to calculate the number of these nuclei in the sample when the corrected count rate was 1,200 counts per second. So if we're looking at the number of nuclei, really we've got to use, and we know the activity, this is the equation we've got to use. So this is the activity at that particular time. This is the decay constant, this is the number of nuclei, so we rearrange it to this. Simply put our numbers in. Activity is 1,200, because it says that in the question here. The decay constant is 1.64 times 10 to the minus 5, which is the decay constant we worked out before. So the activity, so the number of nuclei is just 7.3 times 10 to the 7. So in terms of marking points, basically you got 3 marks for this question, 1 mark for using this equation properly, 1 mark for rearranging it, and 1 mark for showing that you get 1.64 times 10 to the minus 5. In this was worth 1 mark, and this was also worth 1 mark for getting the correct answers. So that was question number 16 of the Nuclear Physics homework booklet.